So for section 5.4, we're going to go ahead and graph the logarithmic functions. The key here is to remember logarithms are the inverse of exponential functions. I'm going to stop for a second. We'll do a couple proofs before we get to the graphing. Here's a quick proof for why we know logarithms are the inverse of exponential functions, because we already know how to get inverses. Let's go ahead and take the equation f of x equals a to the x. This is an exponential function. How would I get the inverse of that? Well, we would take x and y and we'd switch it. So f of x is y. Take this x, take this y, and switch it. We get what? X is equal to a to the y. We are not going to graph it in that form, so we need to undo that exponent. I've already started leading into that. To undo an exponent, we use this log. What does that do for us? Well, the y can travel to the front, giving me log of x is equal to y times log of a. Now to solve for y, we divide by log of a. And then if I use my change of base rules, I can write that as log base a of x. Or the inverse of this f of x is log base a of x. The inverse of the exponent is the logarithm. When we switch x and y and solve for it, you get a logarithmic function. Okay. Keep in mind, with this inverse, the domain, the x, must be positive, cannot equal 0. That has to do with our rules of logs. That means the domain, x must be greater than or equal to 0. Take it a step further if I'm graphing this, because we will be doing shifting as well. So if we have a horizontal shift like that, then basically our domain, x will be greater than whatever h is, will be our domain. Okay, let's continue. So how would I graph 2 to the x? Well, we've done that before. 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4. One side is rocketing upward, and the other side becomes 1/2, 1/4, 1/8. The other side gets closer and closer to 0. So how would I graph log base 2 of x? Well, there's a quick way. You could actually visually switch x and y from the points. You could graph 2 to the x and switch it, since it's the inverse of log base 2 of x. You could sit there and go, okay, well here was a point, 0, 1. If I take 0, 1 and I switch x and y, I get 1, 0. If I take the point 1, 2 and I switch it, I get 2, 1. If I take 2, 4 and switch it, I get 4, 2. What does this do? Well, it creates a function that instead of opening up, opens to the right. And instead of reaching an asymptote on the y-axis, on the x-axis, it reaches an asymptote on the y-axis. And visually, these should be symmetric across the line y equals x. Notice, for our f of x, for our exponential, the domain, x goes left forever, x goes right forever. Negative infinity to positive infinity. The range goes up forever, but it doesn't go down forever, does it? What happens is the range starts at 0 and goes up forever. Does it ever equal 0? No, that's the asymptote, so we put a parenthesis on both of these. So what should the domain and range be on g of x, on the logarithmic function? Well, since we switched x and y, they should be switched. Visually, look at the domain. Look left and right on here's our g of x. Do we go left forever? No. X starts at 0, not equaling it, and goes right forever. Look at the range. It goes up forever, really slowly, but it goes up forever, and down forever. So, negative infinity to infinity. And this should make sense in light of what we talked about before. Visually, I can graph any logarithmic function by graphing the exponential function and switching x and y. That is not how I recommend doing it, but that is an option. And I know some of you probably have been taught that way, and it doesn't hurt my feelings. That's just not how I would do it. Notice There's an asymptote on f of x that y cannot equal 0. For g of x, when x and y switch, x can't equal 0. Okay? Domain and range switch. Even the asymptotes switch. So how would I graph log base 3 of x? Remember, what are we really asking here? Okay? 3 is our base. What power makes x? So I can graph powers. I can pick some x values, and I recommend picking powers of the base. Things like 1, and 3, and 9, and 27, and why? Because I want to go 3 to what power makes 1. That's easy. 3 to what power makes 3. 3 to what power makes 5. That sucks. But if I do powers of the base, if I do 3 to the 0, 3 to the first, 3 to the second, well then, 3 to what power makes 1? 3 to what power makes 3? 3 to what power makes 9? The y ends up just being what the power is, what the exponent is. What happens to the left of here? Well, I can do 3 to the negative 1. I can find what's log base 3 of 1/3. That would be negative 1. 1/9 would be negative 2. This should be plenty of points for me to get an overall sketch of this graph. I have a point 1, 0. I don't get to 2. I'm sorry, I don't get to 1 till we go all the way over to 3. 3 goes to 1. I don't get to 2 till we get all the way to 9. This graph is increasing very slowly. What happens in this region right here? Well, at 1/3 it goes to negative 1. At 1/9 it goes to negative 2. It's approaching that y-axis and creating an asymptote there. We have an asymptote right here that x cannot equal a 0. Okay? So that's the way I would graph it. I would graph powers of the base. You can sketch it and be done. The other option is I can do the 3 to the power. I can do 3 to the 0, 3 to the first, get that overall sketch, and then switch the points. I think that adds extra work. If you understand logarithms, algebraically it's not hard to plot some points and figure out what the graph looks like. What do I do if there's no base? Well, once again, we know that that's called a common log, so base 10. So what values of x will I choose? Powers of 10. Like 10 to the 0, 10 to the first, 10 to the second, 10 to the third, 10 to the negative 1. Why would I do that? Because what log base 10 of 1 is 0, log base 10 of 10 is 1, log base 10 of 2 is 2, log base 10, the exponent ends up being the answer. I can do log base 10 of 5. I just don't want to. I'm picking numbers that I know that are going to come out easy. Log base 10 of 1/10, 10 to the negative 1. So I can graph the point 1, 0. It goes up 2, 3, 4, 5, 6, 7, 8, 9, 10 before it gets to 1. This graph is increasing, but very, very sloppily. How about very, very slowly? What happens here between negative 1 and 0? We already saw it starts going negative. Where's our asymptote? X cannot equal 0. That's how I would graph this. Real quick, I'm going to go back real quick because we need to be able to list the domain and range for f of x, our domain here. We have an asymptote at 0, so x was greater than a horizontal shift. The range, it goes up and down forever, all real numbers, negative infinity to infinity. For example here, what's the domain? X must be greater than the horizontal shift, 0. What is the range? Down forever, up. It is continuing to go up, even if it's very slowly, forever. So it would be all real numbers or negative infinity to infinity. So let's kick it up a notch. What do I do if the base is a fraction? Remember I told you it couldn't be negative, but it can be a fraction. Well, I would choose powers of 1/3. 1/3 to the 0 power, 1/3 to the first, 1/3 to the second. 1/3 to the negative 1 would be 3. 1/3 to the negative 2 would be 9. And then I would do the log of each of these. What is log 1/3 base 1/3 of 9? That is 1/3 to the negative 2. What is log base 1/3 of 3? Negative 1. What is log base 1/3 of 1? What is log base 1/3 of 1/3? What is log base 1/3 of 1/9? I end up with 1, 2, 3, 4, 5, 6, 7, 8, 9. Goes to negative 2. 3 goes to negative 1. 1 goes to 0. 1/3 goes to 1. 1/9 goes to 2. What basically happened here? Well, now the asymptote is going up and it's rocketing to the right. So this gives us kind of a flipped pattern to this. You can still plot the points. How would I generalize these notes? Once again, let me do the domain and range because we're going to keep doing that. Domain x is greater than 0. Range, all real numbers. Well, if our base is greater than 1, this is the overall pattern we see. If our base is between 0 and 1, it reflects it basically across the y. So it reflects the pattern. But what? You can still plot points to see that. What do I do with a natural log? Well, natural log is the same thing as log base e. What is e? 2.71, I think 5, 2.71 something mess, right? Well, I can do that. I can do e to the first power. So that wasn't very impressive. But 2.718 then, okay? So what will I graph? E to the 0. E to the first. E to the second. E to the second. Not pretty, but we can figure that out. E to the second. Sorry, E's, no, that was in the right spot. Let me try that again. E to the second should be 7.389. Why am I picking those numbers? Because the natural log of 1, the natural log of, well, log base anything of 1 is 0. What is the natural log of e? And the natural log of e squared. That's enough to give me a sketch. 1, 0 is still in our points. 2 point mess, 2.7 goes up to 1. 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7 point mess goes up to 2. It looks the same, just a little messier because of the E. But the graph shape itself doesn't change. Still, what is our domain? Well, x is greater than the horizontal shift. Our range, all real numbers. So what do we do if it shifts? Logs were hard enough without shifting them. They're really not that hard. If you can do logs, I don't suggest doing the exponential and switching the points, but if that's what works for you, feel free to do it. I would just choose powers of the base. But sketch the parent graph. Ignore the shifting, stretch and shrink, reflect it, and shift it. Our domain, we've already said, x is greater than or equal to the horizontal shift. The range is all real numbers. So how would we graph this one? Let's see. Ignoring any shifting, our parent graph would be log base 3 of x. I can graph that really quickly. Pick some x's. Log base 3 of 1 is 0. Log base 3 of 3 is 1. Log base 3 of 9 is 2. Alright, I can do better than that. Let's see. This is what our parent graph looks like. No stretching or shrinking, nothing crazy to do there. So all I'm going to do is take this h minus 1 and shift the graph 1 to the right, plus 1. So this 1, 0 becomes 2, 0. This 3, 1 becomes 4, 1. The graph looks the same, just shift it. Now be careful, because if I pulled this a little bit further to the left, I'd mark you off. Because where's the asymptote? Well, the domain, x must be greater than the horizontal shift. X cannot equal, 0 normally, x cannot equal 1 is an asymptote. So you make sure you do not go to the left of that netting, or we're going to have a problem. Last but not least, I already know how to graph log base 3. Parent graph 1, 0, 3, 1. Sketch it out. That is not our final graph. Step 2. Dilate. All of those values get what? Multiplied by? Everything gets twice as tall. The y value here, 0. Well, here, I'll make the table. I don't want to cheat you guys too much here. Two, dilate. What does that do to our table? Well, all the y values are now doubled. So now instead of 1, 0, 3, 1, now it's 1, 0, 3, 2. This graph looks just like the parent, just twice as tall. Step 3, shift it. That minus 1 is 8k. So all of these final points get shifted. I'll use this on a larger, let me change that. So all of these points get shifted down 1, down 1. And last but not least, I draw my solid line. Domain, x is greater than horizontal shift here with 0. Range, all real numbers. Shouldn't be a tough section. Get through, start graphing these. Do the parent graph, do the dilation, then do the shifting.